asked to kind of provide an introduction or just a word of welcome. And I want to, I've been here at Grace for about 2.5 years now as a priest. And when I came in, I thought I was an environmentalist, and I thought I cared about the earth, but I did in a way that many people do. And I've been so grateful for the presence of people like Gary and Marcy, and then their leadership within Earth and Spirit and all the Earth and Spirit folks that call me and have called me during my time here to greater care and commitment on this issue, and greater care and commitment in terms of taking climate change seriously. I feel like they've called me into being a better spiritual being in this world, and I'm very grateful for their presence. And so,
before again I introduce Gary to get started, I want to ask you to take just a moment of what questions do you have?
My concern now is how can we make people get along in a situation instead of killing each other.
So a very big question, and with all the changes, how do we get along without killing each other? Absolutely, a big question.
What can we do other than sitting and talking?
What can we do? Absolutely. Big questions.
Right.
Yes. Any question's a good one. It can be a very small question. Yes, John.
How do we overcome apathy and overwhelm?
How do we overcome apathy and overwhelm? Another one, yes.
With the momentum of the change in climate, how do you, on the bigger scale, how can you, on the Earth scale, how can you slow it down and stabilize it or reverse it? I mean,
sure.
it's a big machine, so.
We're so grateful here, so thank you.
Thank you for that nice introduction, Donna and Eric. By training, I'm an oceanographer, but my vocation over the last maybe 15, 20 years of my career has been using data from satellites to study ocean variability and climate variability. So, and then I took on the responsibility of being the principal investigator for NASA's Aquarius satellite mission, which I'm actually not going to talk about at all tonight. But that's a whole nother topic for another time. Sad news is that Aquarius was launched in the summer of 2011 and performed very well for more than 3 years. And then this past summer, the satellite had a disruption in the power supply control electronics, which killed the satellite. So it's gone inactive. It's still orbiting the Earth, but it isn't doing anything up there. It's just floating around in space. And it'll stay up there for maybe 3 or 4 decades before it finally falls back to Earth, and that will be the end of it. But right now, as far as collecting the data for science, it's over with. But Aquarius was designed to measure the changes in ocean salinity. And we did get more than 3 years of data, and that was our mission requirement, so we actually did achieve our science goals, and so I'm very pleased about that. So it's a success. And but tonight I'm talking more about the big picture, and my goal here, as Donna mentioned in her introduction, is to break this discussion up into 3 pieces. The first is I'm going to bring you up to date on the whole global change picture, where we are in terms of global temperature rise and carbon dioxide in the atmosphere, and just the basic core principles of the science of climate change. I'll talk a little bit about what the IPCC is and what it does and what it's been saying, and I'll talk about the Paris Accords and what came out of that. And then we'll take a break and we'll have some discussion, and then we'll go into phase 2. And phase 2, the focus there is to say what's new since the last IPCC report, which was close to 3 years ago, and what, with regard to the Paris agreements, they've gone a long way in terms of actually, we now have the world community actually focused on this problem and working somewhat in unison on it. That's a big milestone, but is it sufficient to really address the problems in the future? And the answer is no, there's a lot more work to do. So it's not really sufficient, and I'll explain some of that. And that what I'm going to draw from is some research by Dr. Jim Hansen, who's been a real vocal proponent of taking action on climate change, including, greenhouse gas emission reductions and so forth. And then the last part is to talk about what's going to happen to our region, the Puget Sound Basin, and what climate change means to us locally. So that's the focus of tonight. So I'm going to start with this picture here. This is the iconic blue marble, one of the photographs that's been taken from probably one of the lunar missions, I'm not sure. The very first one was taken with Apollo 17, I think. So I'm not quite sure the source. This one actually might be a computerized mosaic of a bunch of other kinds of satellite images. I'm not sure. But the idea is I want to start off with this to say this is our planet Earth. It's our one and only home. And it fosters life. Some people think of it as a living organism in and of itself. I don't dispute that. So I'm going to begin and end tonight with a picture of the blue marble, but the one I'm going to show you at the end is going to have a little surprise associated with it. So this is, if you kind of zoom in on that picture a little bit, you might see something like this. This is probably taken from one of the space shuttle or space station missions. This, you can see here the haze of the Earth's atmosphere, and then you can see the moon in the background. I use this image because I want to get across a point here to you, and that is that the atmosphere around the Earth is really a very thin layer. If you think that the Earth, if you can imagine the Earth shrunk down to the size of an apple, then the thickness of the atmosphere would be thinner than the skin of that apple. So it's a very thin and a very fragile layer. It's not infinite, and we can't continue to fill it up with garbage forever because it gets polluted. We know a lot about air pollution. So that's the point, is that the atmosphere is something that we have to protect for our own sake. So here's a record of the changes in the Earth's temperature from the mid-19th century to the present. Actually, this chart goes through the end of last year. And if you want to know where 2015 fits on this chart, that little star that just popped up on the right, it's just a little bit off the chart. So we've gone up another couple of tenths of a degree Celsius just in the last year. But the trend is clear. Over the 19th century, global temperatures were pretty steady. The gray zones here indicate the degree of uncertainty of the measurements. So there's a lot of data that are collected. There's a lot of variance and uncertainty in those data. And so when you do an average, you get this line in the middle, but the gray zone tells you what the distribution is of the variance of that data. And as you can see, as time goes on, the gray zone gets smaller and smaller and smaller. So we have much better confidence in our measurements in modern times than we did from 150 years ago, as you might expect. There are three different institutions that track these global temperatures, that are primary ones. The Meteorological Office in the UK, it's called the Hadley Center, our National Oceanic and Atmospheric National Climatic Data Center, and then NASA's Goddard Institute for Space Studies, which is where Dr. Hansen worked until he retired a couple of years ago. They all gather all the temperature data that are available from the ocean, from ground meteorological stations from around the world, and they do different ways of quality control and assessing that data and averaging it together to come up with a world average. And as you can see, the black curve, the yellow curve, and the blue curve are very close together and closely matched and well within the range of uncertainties. So basically, they're all giving us the same essential information. There's very little debate that the temperatures are actually rising. This diagram here is produced by NOAA, the vertical axis here is the change in temperature from a certain reference point, 20th century average in degrees Celsius. So this is 0 change, and this is 1 degree Celsius change. And then the horizontal axis is the month of the year. So, and you can see there are curves for different years, 1998, 2009, 5, 11, 10, 2014, 2015, each with a different colored curve. So if you average the temperature over the year up until a certain month, so if you start off here and you just look at average of January, you get this number here. If you average January and February together, you get the next number, and so on and so forth. So by the time you get to the end in December, you've averaged over the whole year for that particular year. So these are just showing that most of these previous record-setting years are all clustered pretty closely together, around 0.6, 0.7 degrees Celsius. In 2015, we're up over 0.8 degrees Celsius, almost to 0.9 degrees Celsius by the end of this year. So this past year is the warmest one on record in terms of global averages. That's where we are. Okay, so there's 2015. This is a map of temperature change over the continental United States. This is a map that's put out by NOAA. Because it's a US agency, they have to use Fahrenheit instead of centigrade when they put these things out to the public. So now we have to switch gears and think about Fahrenheit degrees instead of Celsius degrees. And I don't have a color scale here, but the reddest colors, and you can see pretty much the whole West and most of the Midwest, is colored the darkest red, which means for 2015, this was really quite warm relative to the average, and it's a little bit better in the Midwest and the East Coast. And so that's no surprise that the West has been hot for the last year or two. 2015, in terms of just the continental United States, ranks second overall. The warmest was 2012. But anyway, 2015 was a hot year in terms of the climate. So where is this all coming from? This is the time series measurement of carbon dioxide from the Mauna Loa Observatory. I imagine many of you have seen a picture like this before. There's two curves here, a black one and a red one. This is the scale of the concentration of CO2 in the atmosphere in parts per million. It started off in 1960 at less than 320 parts per million. And that now it's just over 400 parts per million. And that, when you think of that in in terms of a percentage, it feels like a really small number, but it isn't that small in terms of the impact that carbon dioxide has on the radiative budget of the atmosphere. Now you see there's a sawtooth pattern to these red curves. This basically is one up and one down each year, and that has to do with the seasons, and that's because in the spring and summer, the foliage in the northern hemisphere blossoms out and the trees grow leaves and they soak up a lot of carbon dioxide. And so there's a transfer of CO2 from the biosphere to the atmosphere, back to the biosphere, that's driven by the seasons, and you see this oscillation in the concentration. But if you accumulate this over time, you can see there's a very persistent trend in what's going on. The Intergovernmental Panel on Climate Change is something that's basically sanctioned by the United Nations. All member states of the United Nations participate or can participate in the Intergovernmental Panel on Climate Change. So it's an international body. It's made up of scientists and not only physical scientists and climatologists, but social scientists and so forth. And there are three working groups within the IPCC. One of them is Working Group 1, and their job is to focus on the description of the climate, the state of the climate, what's going on. And then Working Group 2 looks at the impacts, the societal impacts, and Working Group 3 looks at mitigation strategies. So most of my attention is focused on Working Group 1, just trying to understand the science a little bit more. And each year, they put out a summary for policy managers. And so back in 1990, when the first assessment was conducted, and the other thing I want to point out is this is a political body. There's a lot of science behind it, but all the wording of everything they write in their reports and their summary for policymakers has to be agreed on by all the parties. And not everybody has the same nuance that they want to put to the words. So there's a lot of diplomacy about the wording that goes into some of these statements. So the very first one was that emissions from human activities are substantially increasing the atmosphere concentrations of greenhouse gases, and that this will enhance the greenhouse effect and result in additional warming of the Earth's surface. So that's 1990, so that's 25 years ago. The second assessment, 1995, the wording got a little stronger. Greenhouse gas concentrations have continued to increase. The balance of evidence suggests a discernible human influence on global climate. Climate is expected to continue to change in the future. The third assessment, 2001, there's new and stronger evidence that most of the warming over the last 50 years is attributable to human activities. Human influences will continue to change atmospheric composition throughout the 21st century. Global average temperature and sea level are expected to rise. So as you can see, as time goes on, the wording gets stronger and stronger. So the fourth assessment was in 2007, almost a decade ago. The understanding of anthropogenic warming and cooling influences on climate has improved since the third assessment, leading to very high confidence, meaning more than 90%, that globally average net effect of human activities since 1750 has been one of warming. So basically they came out and said, yes, human beings are warming the planet. All right? That wasn't until the fourth assessment. So you can see the influence of the diplomatic process here. It's a political process. But when we got to the fifth assessment, which was published in 2013, now it says the warming of the climate system is unequivocal, and since the 1950s, many of the observed changes are unprecedented over decades to millennia. The atmosphere and ocean have warmed, amounts of snow and ice have diminished, sea level has risen, and concentrations of greenhouse gases have increased. So the wording has gotten stronger. So that's, as of 2013, this is basically the statement of the IPCC assessment, and it's based on these results and the very thick volume that they produced that analyzes all of the physics of the climate that drove the discussions in Paris. Okay, it was based on these assessments. So some key points of the Paris Climate Pact, all of the negotiations that we were all watching closely a month ago. First of all, it calls for holding the increase in global average temperature to well below 2 degrees C above pre-industrial levels. And pre-industrial levels, we can say maybe the mid-1700s, before the Industrial Revolution in Europe. Countries should reach global peaking of greenhouse gas emissions as soon as possible. So for any nation like ours, our greenhouse gas emissions have been rising too as an individual nation. We need to start reducing emissions so that it will will reach a peak and then start to decline in the future. And so the mandate is for all the participating countries to come up with a plan to peak their emissions as soon as possible within the next decade if they can do it. Acknowledges the importance of averting, minimizing, and addressing loss and damages associated with adverse effects of climate change. And there are a number of developing nations who are at the conference who are advocating for their position because they live on a tiny island and sea levels are rising, or for some other reason they're being adversely affected, maybe by drought or some other something that's really important to their livelihood. So some compensation or some way that has to be addressed, that's part of the accord. Each of the participating countries have agreed to submit updated plans that would ratchet up the stringency of emissions by 2020 and then every 5 years thereafter. So there's a plan now in place that by the end of this decade, all the countries that participated in this negotiation are going to come up with a plan, and that plan is going to be reviewed on a 5-year cycle to see how well they're doing in matching their goals. So this basically is keeping everybody's toes on the line, and that's a good thing. It's not that we had a big meeting and we went away and we're all happy with what we discussed, but there's actually a plan to do something about it. It sets up initiatives to help developing countries meet new requirements, and then when countries update their commitments, they will commit to the highest possible ambition. That's an interesting choice of words, but the agreement does not specifically set numerical targets. And I think this was a compromise that had to be worked out amongst a number of parties I know that what I've been reading in the press is that on the U.S. side, there was a strong push not to commit to any specific binding agreements for political reasons in the U.S. because otherwise it would have been considered a treaty. It would have to go to the Senate for approval, and the President and the Secretary of State did not want to go down that path. So they worked very hard to keep the wording to something that could be continued to be managed at the executive level without having to go through some kind of political approval in the Congress. And I think they succeeded. Okay, I have a little animation that I'm going to show you here. And I'll explain to you what's going on here. This scale here is the concentration of carbon dioxide in the atmosphere. This scale here is latitude, so this is looking at global averages depending on what latitude you are. Here's the southern hemisphere here, here's the equator, the northern hemisphere. You can see, and this is over time, so you can see things going up and down with the seasons, as I explained earlier, and this is accentuated in the northern hemisphere. And you can see the trace over here over time. So here's 1980, 1984, 1988. So time is proceeding to the right, and you can just watch as each year goes by. This is the South Pole here, the blue dot, and it's slowly creeping up. There's very little seasonal cycle here compared to what we're seeing in the northern hemisphere. And all the dots that you see on the map are the locations of the observations that go into creating this graph. And it just keeps on zigzagging up and down. You can see there's a lot of variability in some places. And here, this little thing that popped up, it was in October 1989, I think, where we passed 350. And 350 had for a long time been a benchmark where we said if we want to keep temperature change under 2 degrees Celsius, we have to keep carbon dioxide under 350. It's been a long time since we surpassed that in terms of CO2 concentrations, and we are now actually higher than 400. And so getting back down to 350 is going to take some real work. So this little cartoon is just about over, and you can see that in the northern hemisphere it's up above 400, not quite there yet at the South Pole, but very close. So there's one more little part of this thing. So here, this is looking at some paleo data going back before actually these are still Mauna Loa records before, they go all the way back to the mid-50s. And now we're looking at paleo data. So all of a sudden the scale changed, and we see this going back in time, it drops way off. So in 1800, the concentrations were less than 280 parts per million. And so here, pre-industrial times, 278, 335 in 1979, 398 in January 2014. And now what we're looking at is data that's recovered from ice cores. And that goes back thousands and thousands of years. And when this thing is finished playing out. So here's the most recent interglacial period right here, where carbon dioxide levels went up, and so did temperatures. This is a glacial period where the temperatures are low, and then interglacial here. So by the time this is finished scrolling, we'll have gone back about 800,000 years in history. And you can see during that entire time, all the carbon dioxide levels have consistently stayed less than 300 parts per million, and now we're basically 30% higher than that, over 400 parts per million. So I think that's the end of chapter 1. So we can pause now for some discussion. And Donna, do you want the microphone?
Thank you, Gary. I think I'll continue to just speak up. Thank you, Gary. So the question we'd like for you to now ponder individually for just a moment is, what did you learn in this first section? What really stood out to you in this first section? The rate of change appears to be, I noticed that too, seems to be greater in the northern hemisphere. How many of you took note of that stood out to you? Yeah, interesting, isn't it? You, Gary?
Well, there's a pretty clear explanation of that. Most of the industrial emissions are in the northern hemisphere, so the concentrations are higher, and then the acceleration is higher as well.
But what really surprised me was to have the South Pole just...
It's just being dragged along with everything else.
The whole
Yeah.
system, it's part of the system.
The whole system is, I mean, the atmosphere is well mixed. If we stopped emissions, then it wouldn't take very long for the atmosphere to be pretty homogeneous in terms of the concentration of CO2. But we're constantly pumping in one hemisphere, and it takes a while for it to filter down to the South Pole. Yeah. It'll take time, a long time. Yeah, it's also very persistent in the atmosphere. Right.
I appreciated you including a couple slides demonstrating the evolution of the policy language, or the language that went in, reminding us that it is this combination of science but also human debate, discussion, and ultimately agreement. And I was encouraged that
Yeah.
slow as we might view it now, was going the direction it has to go.
Yes. Yes.
Yeah, I think that the facts, all the facts that you presented here are what really is compelling, that everyone's known since the 1990 that there was climate change being caused by human activity.
Yeah.
And it's taken so long to get the awareness that that is really true. And there are political people who still deny it.
Oh, yeah.
I don't think that it's proven. It's just astonishing. But, and the information you gave just so well verifies.
A tree pattern of CO2, what's going on there?
Her question was, why doesn't the southern hemisphere have much of a seasonal, as a large amplitude of a seasonal cycle as the northern hemisphere?
You're still not on.
The fraction of the Earth's surface covered by ocean in the southern hemisphere is a lot larger, and it's mostly the respiration of the land foliage that causes that. There is a seasonal cycle of primary productivity in the ocean, but it doesn't have that kind of amplitude in terms of the CO2 flux.
Okay, we have two more, Eric and then Beulah, and then we're going to.
I think what was helpful is that you're accounting for, because climate deniers, one of their basic arguments is that, well, there's always this natural fluctuation, right? And that's how they dismiss a lot of this. And so you're accounting for the natural fluctuation over time, glacially and in the interglacial periods, but then also seasonally. And so to be able to see that accounting and then put against the human contribution, I think was particularly effective.
So, most of you have probably heard of Jim Hansen. He's kind of an icon of spokespeople for climate change. He started running some experiments. There were other scientists at Princeton and other labs that were doing the same sort of thing. And he came to Washington in 1988, and it just happened to be the same year that Marcy and I and our kids moved to Washington, and I started a 2-year job at NASA. And he testified before Congress, and he basically said, folks, it's happening. All right, climate, and this is back in 1988, and he had results from his numerical modeling studies and indicated that it was definitely going on. And it really got the public awareness ball rolling a lot. And he's been a very persistent, outspoken player in this scientific process, and in some cases the political process over the years, and has written a number of very insightful papers. And he's a member of the National Academies of Sciences, and a number of his papers are published in the Proceedings of the National Academy. So it's very prestigious work. And he's just completed a study. It was published in a kind of obscure atmospheric chemistry journal, but it's an online journal, so you can go and actually look at it. You don't have to be a subscriber to the journal to get access to the paper. And the key points, one of the key findings he has in this is that he has analyzed, and I'll explain his approach here in the next couple of slides, but he's basically said, you know what, folks, even what the IPCC has said in its last assessment, which was just 3 years ago, is insufficient. Okay, this is going to happen. Things are going to be more severe than what the IPCC has been projecting. So that's a big red flag that goes up. Then a couple of other new science topics I want to touch on here are ocean and ice sheet interactions. By ice sheets, I mean the Greenland ice cap and the Antarctic ice cap. and then also the effect that global temperature change is going to have on creating a more arid landscape worldwide. So these are the three topics I'm going to cover in the What's New in Science. So this is a picture here similar to the one we just saw in that cartoon. And here's my new microphone. Okay, are we on? All right, we'll do that. Okay, so this is again the same graph that you saw in that cartoon right before the break, and the time axis is backwards. So on the left is it's in the past, but the scale here, this is 800, 700, 600, 500. These are thousands of years. So this is 500,000 years ago. This is 800,000 years ago. So this is almost 1 million years of history of climate. And where this data come from are from ice cores. And basically, some very clever scientists have developed this technology over the last 10 or 15 years. Basically, they go to some of the highest altitudes on the Greenland ice cap or to Antarctica with a big drilling rig, and they bore a hole down through the ice and pull up this core of ice, take it into a lab, and very carefully, you can see the layers in the ice like tree rings. Each year there's a little bit more snow that's laid down, and so you can count backwards in terms of the years, and then you can pull out some of the ice, and there are little bubbles that are trapped in the ice. And those bubbles capture the composition of the atmosphere at the time that the snow fell on that ice cap. Okay, so you can count back in time and see how long ago this happened, and then you can analyze the air that's trapped in those tiny bubbles, and so you can actually measure the concentration of carbon dioxide trapped in those ice cores, and that's what this blue curve is, and you can see it going up and down, up and down, up and down over time. And then there's another curve here, it's labeled temperature, that's the red curve, and that's, the scientists can look at the isotopic ratio of two different oxygen isotopes, and the amount of the heavier isotope that gets trapped in the ice is also dependent on temperature. So by looking at the ratio between regular oxygen 16 and oxygen 18, you can get a proxy for how the temperature has changed over time. So that's how they reconstruct the temperatures. It's really interesting work. So what we see here, something's supposed to pop up. Yeah, okay, so the interglacial epochs. So each one of these upward branches of this time series, each one of these peaks is what's called an interglacial. So that's when the climate was warm, pretty much like it is right now. And all of these lower ones here, these valleys, instead of the peaks, the valleys, these are the glaciations. You can see that the glaciations, like take this example here, they tend to last longer, and then there's a sharp rise in temperature and carbon dioxide till you reach the peak, and then there's a gradual decline again. So the last interglacial was about 120,000 years ago, and that was called the Amian. I guess that's how you pronounce it, E-M-I-A-N, interglacial period. It was about 120,000 years ago, and I've got that highlighted in red right here. And what Dr. Hansen has done in his study is he said, what can we learn from what we know about this interglacial period, the last one that we had? We're in an interglacial right now. This is the current, the Holocene period is this rise in temperature that occurred over the last 15 or 20,000 years, and we're pretty much at the peak of it right now. So what can we learn about the last one that can give us some guidance about what might be happening now, particularly with carbon dioxide, anthropogenic carbon dioxide? So a little bit about the Amian interglacial period, 120,000 years ago. The peak temperature was actually a little higher than it is today, about 2 degrees Celsius. But the carbon dioxide concentration stayed below 300 parts per million. So even though carbon dioxide is, what Hansen calls it the control knob of climate, you can have a situation where there are other factors in the climate system that are help pushing the temperature up that are being affected by carbon dioxide. So the question is, when we get to 400 or even 500 parts per million, what kind of risks are we looking at? And the other thing he points out is that sea level during the Eemian interglacial period was at sometimes several meters higher than it is today. So he's projecting that we have a strong likelihood, a high likelihood, that we're going to see even higher sea levels than we have right now. So I'll go into some of those results here. I'm not going to show you a lot of diagrams here. I basically just have some bullet points here. But what he does is he goes and he looks at the paleoclimate evidence from the previous interglacial, which I just described, and he looks for indicators from that what the future scenarios are for the current epoch. And then he goes and he uses his climate model to analyze the past events and infer if these kinds of processes are going on now, what impact that's going to have in the near term for us. And then he highlights some of the significant threats. So I'll explain what those are. So basically what I have highlighted in red here is he's basically proclaiming at ice melt, sea level rise, and superstorms, evidence from paleoclimate data, climate modeling, and modern observations indicate that 2 degrees global warming is highly dangerous. Okay, so trying to hold it to 2 degrees is not going to do the job. This is still too dangerous. And this is just a citation of the paper. If you want to look it up on the web, you could go to that website and read the whole thing yourself. So he points out that the goal of limiting global warming to 2 degrees Celsius is insufficient to avert major climate disruption. He says that ice sheet mass loss can yield sea level rise of several meters within 50, 100, or even 200 years. So we may be looking at several meters of sea level rise still yet to come, which is a little unnerving for me and my wife because we live down on South Beach Drive, and I did a survey a while ago, and from the current high tide level to my garage door is about 22 feet. So that's, about 7 meters or so, a little bit under 7 meters. So there's not a whole lot of margin there, and that doesn't even account for a strong, 50-knot south wind that we get all winter long. And he also believes that rapid large sea level rise may begin sooner than generally assumed. So he's looked at the paleoclimate record, he's run his model simulations, he can recreate that same kind of variability in his model, and he looks at the processes, and they're connected with the melting of ice sheets in 2 ways. So when the ice sheets melt, they, of course, add water to the ocean, but they also change the circulation of the ocean because that fresh water flooding over the subpolar regions affects the ocean circulation, and that can actually bring more warm water up into the higher latitudes and speed up the melting of the ice. And so it's the interaction of these ice sheets and the changing global ocean temperatures that are the real key factor here. And that's one of the things he points out in his study. Okay, a couple of other things. He basically thinks that rising sea levels, and the other thing he's found out looking at paleoclimate data and in his model, is that under these changes in the ocean conditions, it's ripe for more devastating storms, and particularly in the temperate latitudes like where we are. So stronger storms coming off the Pacific would be more likely under these scenarios. So we got increasing sea level and more severe weather, both in the projection of what he's looked at in this recent study. And then the final point he makes is a little bit more subtle, but he says that instead of trying to define a guardrail, he calls it a guardrail of 2 degrees Celsius as a temperature change, he said what we really need to do is use fossil fuel emissions as our metric, and that's what we should work for, and reduce those as fast as possible, and not fritter around with trying to look at whether or not this is going to achieve a 2 degree C temperature rise or not. He basically thinks that the danger is imminent enough that we really have to change our focus and get away from temperature change and really just look at emissions and deal with that directly. Okay, so I'm going to use this animation from NASA to illustrate a point for you. So what we're going to see here we're looking at ice streams. And basically, some really clever data analysts that work for NASA have taken a series of satellite images over Antarctica, and by looking at pairs of images separated in time, you can actually see where the features on the surface of the ice have moved. And so they can recreate these trajectories and actually create this movie of streams of ice. So glaciers are basically like very slow rivers. They do flow, and if I can get this to go again, I'm going to stop. Yep, it's going. All right. All right, I'm going to pause it right here. If I can do this, I'm going to stop right there. Okay, paused it. All right. So you've seen the motion picture. Now I want to look at the still life. So these are the major ice sheets that are colored in purple here that are really moving fast. So the parts of Antarctica that are contributing to sea level right now are all these purple areas. And as you can see, they all have pretty substantial openings to the ocean. So it's the interaction between ocean and ocean temperatures and this glacial ice that's moving down towards the sea that's one of the factors that's really driving sea level. And what's happening basically is warmer water from the ocean is intruding up onto the shelf and melting this ice more rapidly than it has in the past. So changes in ocean circulation, changes in ocean temperature are coupling with the glaciers and causing them to melt more quickly at the mouth. And then once the melting takes place, these glaciers can actually start to flow faster because they're not being blocked by the ice that's reaching the sea. And so they speed up. And just a month ago, I was at the American Geophysical Union Science Conference in San Francisco, and there were a number of sessions devoted to this process. So there's quite a bit of new research that's being done on this right now, because this is one of the big wild cards in the climate. Not much is known about these processes. We know sort of conceptually what's going on, but the details are going to require a lot of observations. Scientists are going to have to go out and measure currents and water temperatures in these areas and couple this with satellite data and do a lot of work on this to really understand and put some concrete measurements into how fast these ice sheets are flowing. And the same thing's going on in Greenland too. So I'm just using Antarctica here as an example. Okay, so just a couple of points about ice sheet ocean interactions. This ice sheet stability is regulated by ocean temperatures at the mouths of the glaciers. Increasing ocean temperatures can accelerate the flow of ice sheet as they enter the sea. And this is a focus of new research in Greenland and the Antarctic. These processes vary a lot from one glacier to the other. A lot of it, the topography of the land under the glacier, it goes down a valley, it carves out a valley, creates a fjord, dumps a lot of sediment, and so there's a lot of physical blockage to the glaciers. So how fast they're actually going to move is very difficult to predict. Glaciologists have a wide range of opinions about this. But there is, according to Hansen's study, and I had to read over this a bunch of times to really comprehend it in his paper, but basically he's saying that the fresh water as it flows out onto the ocean influences the circulation enough that it brings more warm water up in contact with the glaciers and then can accelerate the melting. Then you get more fresh water, so you can get into one of these instabilities that can accelerate the glacier loss. This is one of the things that his modeling studies indicate. In addition to that, there's a new study that just cropped up just last week. Some folks that have been working on the Greenland ice sheet have been measuring the rate of melt at the surface, at the top of the glaciers. And what generally happens is that as the surface, most of the glaciers are topped with fresh snow. As that melts, the water kind of trickles down and fills into the spaces between the snow, and then that refreezes and it kind of traps the water there. But what they're saying is that once this happens a few times, then the water's got no place to go, so it starts to run off. And so there's an accelerating runoff of surface melt water from the tops of the glaciers as well, and that's adding to the rate of sea level rise to some degree. And so there are two processes that are going on at once. Okay, now the last topic I want to show you here. This is a complex diagram, which I'll walk you through it a little bit. I was lucky enough to go to a seminar at the university last year, well, actually a year ago, October, by this Professor Chang Fu from the University of Washington. He's actually an atmospheric scientist, but he's gotten into this idea of understanding a parameter called aridity, which is basically how arid the land surface is. And there's been some work over the years, over decades, of trying to understand. It's not just drought, but it's more about what are the factors that determine how arable the land is. And basically, there are two factors that go into this calculation. One is surface temperature. So this is a map of change of surface temperature under one of the climate change scenarios between from 1961 to 1990 as a base period until something 100 years later in the climate models. And then there's this other diagram over here, which is something called potential evapotranspiration. Now, that's a long word, but what that basically means is, well, you know what evaporation is. Transpiration is when water is drawn out of plants, plant tissue, leaves. So evapotranspiration is a combination of water loss from the surface, both from the soil and from the plants themselves. So imagine your garden doesn't get watered for a couple of months in the summertime and you go out there and everything's turned brown. All right, that's because of the evapotranspiration in both the soil and in the leaves and the plants in your garden. So if you calculate this term, potential evapotranspiration, you can take the ratio of the precipitation to the evapotranspiration, and you basically get a ratio of the water coming in versus the water going out. And an arid region would have a ratio of maybe 10%. Okay, so the desert, the southwest of the United States probably has this ratio, P over PET, this number right here, of around 0.1 or so. So what he's done is he's calculated using the climate models from the IPCC, what's this going to look like in the future? And so here's the change in temperature, here's the change in evapotranspiration, here's the change in rainfall, or precipitation in general. It could be rainfall or snowfall. And all the areas that are colored green here are going to get more moisture under the climate change scenario, and the areas that are colored pink are going to get less. And you can see it looks like, you know, much of North America is going to benefit from additional rainfall under climate change. But when you actually calculate this balance between precipitation and evapotranspiration, you get this calculation over here. And basically, all the areas that are colored pink here are going to be more arid in the future. And so it's going to be less arable for food production. And this covers, you know, most of North America, large parts of South America, Western Europe, and so a lot of the food-producing areas of the world are going to be suffering if these projections, you know, come true. And he's using this scenario RCP 85, which is one of the most extreme carbon dioxide emission scenarios. So this is considered to be kind of a extreme case, but I think it's pretty scary myself, okay? I mean, imagine the United States not being able to produce enough food to feed our own population.
Africa will feed us.
What's that?
Africa will feed us.
Africa will feed us. Well, it may look like that here, but I don't know. Well, you know, Dennis, it looks like the Horn of Africa and area around Ethiopia is doing okay in this projection. It's still green over there, but lots of the rest of Africa is not. So, of course, these are the desert areas already in the southern part of the continent. Australia looks pretty grim. So, I mean, these are preliminary calculations. There have been a couple of published studies, this one published in 2013, and another one that appeared in Science magazine. So these calculations have gotten some acceptability, you know, in the peer review process. So this is something really to watch. And to me, it's you know, ice melt is an important concern. I'm worried about the sea ice, you know, disappearing from the Arctic Ocean, sea level rise and so forth. But food supply is pretty near and dear to what we need to survive as a species. So I think this is a pretty alarming result. Let me see. Are we at the end of our stage 2? I think we are.
I just had a question, knowing that I mean, in those interglacial cycles, I mean, over the eons, the hundreds of thousands of years, when the Earth does cool and it gets really colder, we had no real understanding of how did. I mean, so naturally there is a way things get colder. Does that provide any hope for us that the natural systems, there is a cooling process? How does that happen?
Well,
How do those glacial cycles work? They're tied to orbital cycles of the Earth and variations of the tilt of the Earth's axis over time. And what really drives it is, the Earth's orbit around the sun is kind of elliptical. So there's one period of the year when you're closer to the sun and another period of the year when we're farthest away. And so when you're further away, you're getting, the sunlight is a little bit attenuated, so you're not getting quite as intense solar radiation. And then whether the Earth is tilted towards the sun or away from the sun in the respective hemisphere that's having the summertime. And what that does is determines whether the winter snowfall can survive the summer or not. And so it's the amount of insolation that you have in high latitudes that really governs that. And that's actually a very predictable thing that can be calculated quite easily. And so as you get more insolation in the high latitudes in the northern hemisphere, you tend to warm things up because you can melt off all the snow cover in the summertime. And then as that declines, then it's cool enough in the summers that the winter snows may last over the summer, and then next year you get more snow, and you start to build up ice sheets, and that's basically how the ice sheets progress. So the orbital cycles of the Earth around the sun and the tilt of the Earth's axis, these cycles, there are various periodicities. There's a 20,000 year one, a 40,000 year one, 120,000 years, and so on. Those are kind of like the triggers. But then there are feedbacks within the Earth's climate system that amplify those signals, and that's what drives the glaciations. And the cooling off actually takes longer time, and then it stays cold for many tens of thousands of years, and then there's an abrupt warming. So to answer your question, does it offer any hope for us? If all things were happening as a natural process and there weren't any anthropogenic influence, then we would be near the peak or past the peak of this present interglacial, and the glacial cycles would start to be moving us towards a colder climate. But the anthropogenic CO2 forcing is pushing it the other direction. If we didn't have 400 parts per million of carbon dioxide in the atmosphere, we probably would be on a cooling trajectory, or starting to. Yeah, Janet.
Climate deniers sometimes point on to.
Yeah, but it isn't going to happen to reduce CO2 in the atmosphere.
Right. I was just adding to your statement, Gary, that what the things I've read is that we basically canceled the next ice age because we are.
Well, we're at least postponing it.
Yes, right. Because look, we're mining the sea caps, and they're, the ice caps are. Mm-hmm. There goes those layers. There goes that.
Yeah. So. I mean, that is the situation. I mean, on the geological time scale, the Earth ought to be cooling off right now, and we're pushing it to dangerous levels of warming instead. So we do have a pretty strong influence. Yeah, I think it's, I mean, you can think of it as sort of a geoengineering kind of process, but I think the uncertainties are pretty high. This thing could go out of control one way or the other. And it depends on how long the plateau of this current warm period would be. I mean, this Holocene's already been going on for 10,000 years. That's a pretty long time period. But humanity has enjoyed a relatively stable climate for a very long time, and I guess we would like to keep it that way. So, you have a good point. Avoiding an ice age might be a good thing. So there'd be more waterfront property if the sea levels drop another 100 meters. Okay.
Let's go into the third section about
local. Okay. So we're going to move it from global change to more local issues now. And I want to give Marcy credit for taking a lot of time over the last few days to really read and absorb this report, which was just published in November, this past November, by the Climate Impacts Research Group at the University of Washington. And this is a group of scientists and faculty members at the University of Washington that have joined together to form this special group that's focusing on what does all this climate change mean to the Pacific Northwest. And in 2009, they issued a report that looked at the whole Northwest region, Washington, Idaho, Oregon, parts of California, maybe western Montana. This latest report is focused on the Puget Sound Basin. And so that's what we're going to talk about a little bit here. And Marcy put together a lot of this material, or she helped me put it into this PowerPoint presentation. So if I miss something important, she's going to remind me to make sure I mention it. But so the first point to make about this study is things are changing. So the future is unlikely to resemble the past. Though we're used to a certain climate around here, we're used to a certain amount of snowfall in the Cascades and getting up into the mountains and going skiing. We're used to fresh water supplies in our watersheds and so on and so forth. But things are changing now, and changes in the climate is going to be warmer in this region. There'll be changes in the timing and the amount of stream flow, changes in our landscape, and the Northwest's hydroclimate. And I think what we mean here is the whole hydrologic cycle in this region, how much precipitation we get, the soil hydrology, and so forth. It's going to be more dynamic as time goes on.
What is dynamic?
Dynamic? Variable. So this is, what this group did was looked at the climate prediction models from the IPCC assessment of 2013. And this is a graph of temperatures over time projected by these models for this region based on two of the scenarios that were considered by the IPCC. And of course, the black horizontal line is historical. This goes from 1950, here's 2000, here's 2025, and it goes all the way up to 2100. So this black section here is all observations, and then the blue and the red curves are predictions from the ensemble of climate models. And again, like I explained in an earlier figure, all the fuzzy lines that you see here give you the dynamic range of the different predictions. So it gives you an idea of how much confidence there is. There's more confidence when these fuzzy lines are close together, and when they're really spread out like they are out here, there's less confidence in the predictions that far into the future. But there's two different scenarios here. This is the most extreme carbon dioxide forcing of all the IPCC studies, and this is one of the more moderate ones, the blue curve here. So even with the blue curve, and again, the temperatures are given in Fahrenheit instead of centigrade, but we're talking about 5.5 degrees Fahrenheit difference, which is a few degrees centigrade. So already we're talking about more than 2 and probably 3 to 4 degrees centigrade climate change, even under this more moderate scenario. And the other point to make is that these two curves are pretty close to one another. In other words, you couldn't really distinguish them because they're both within the range of uncertainties until we get to about the middle of the century, and then they really diverge. So the effects really pile up over time. So the second half of the century, we're going to see much different effects depending on which of the two climate forcing scenarios we're faced with. This is a map, two maps that show the whole Puget Sound Basin watershed cascades. You can see the outline of Washington State right here. This is the Washington-Oregon border. This is the Puget Sound right in here. And so you've got lots of blotchy colors on this map. So this is depicting mean surface air temperature and maximum stream temperature. And here's a temperature scale down here. And so we got Celsius and Fahrenheit here, whichever flavor you like. So all the yellow colors are temperatures are being reached where it becomes too warm for salmon to thrive. They can't get upriver if they're spawning because the water's too warm, or the smolt and the young salmon have difficulty getting downriver for the same reason. So here, in the historical time, 1970 through 1999, there's a whole lot of area east of the mountains that's too warm for salmon to thrive, and the areas that are colored pink and orange are even worse. And then from in the 2040s, under one of the median forcing scenarios, you can see there's a lot more area that's covered with red colors that it's just too warm for salmon to thrive. And then all the dots that you see here follow the same color scale, but those are actual samples in certain streams as far as we can deduce from the report. And so the take-home message from here is that it's going to be much more stressful for salmon to thrive, as time goes on, and you know, that's not a good thing for our local ecosystem. All right, this diagram here show seasonal cycles of rainfall, and it looks at 3 different watersheds. The Yakima River watershed, the Columbia River watershed at the Dalles, and the Chehalis River at Porter. And there are 3 different types of watershed here. This one here is dominated by rain, and the different climate change scenarios are depicted by these different colored curves. So for the rain-dominated picture, the peak, this is the river flow, okay? The peak is going to occur February to March in any of these scenarios. So in the rain-dominated ecosystem, there really isn't much change that's predicted. In a snow-dominated one, there is a shift. You see that under the different warming scenarios, the warmer you get, the more there's a shift towards the winter from the summer of the peak runoff of the river, and that's because the snow is melting earlier in the year. And then if you look at a mixed rain and snow watershed like the Yakima River, so this is what the current peak runoff is, which is in the middle of the summer, but under the extreme climate change scenario, the peak runoff will be in January or February. So this is, again, another way that salmon could be severely impacted, because some of the species, their spawning runs for Chinook in particular are usually in the summertime, so this could be really disastrous for that particular species in this watershed. So these are just some of the examples of how the hydroclimate is going to be changing. Flooding is another big issue, and here we're talking about flooding from 2 perspectives. One is that you get more rainfall and more snow melt, and so the water tables rise, and there are areas of the state that experience a lot of flooding. And the other is that sea levels are rising. Storminess, severe weather could be increasing. Storm surges with higher sea levels will extend farther inland, and so they'll affect more areas of the coastline. And winter storms are expected to be higher intensity. So a combination of these factors are going to threaten a lot of things. Our transportation infrastructure, for example, the ports, the ferry docks, are going to be impacted by sea level rise. There was even one mention in the report about parts of Boeing Field could be impacted by sea level rise. Sewage treatment facilities, agricultural dikes, shorelines, drinking water resources, and these are situations even around here on Bainbridge Island where some of our aquifers already have some effect of saltwater intrusions, and this could get a lot worse as sea level increases. So there are going to be impacts on our daily lives from some of these things. This chart here comes from this report, and it illustrates the changes in the risk of fires, wildfires. And of course, the brighter red color, the greater the risk is. So the highest, so here we have Washington, Oregon, Idaho, western Montana. This must be Wyoming over here. So there are areas where the risk of fires is going to be 600 to 700% higher. That's quite large. And then, you know, the different colors, you can read the key over there. This area, this strip over here that encompasses Puget Sound does not mean that there's no risk there. It's just that it was not considered as part of the study, so there's no data or no modeling to add to this figure. So, was there a question?
Kat said, could you say that again? About
Okay, yeah, this gray strip right here doesn't mean there's no risk. It just means that it wasn't modeled as part of the study. They just left it out for some reason. Okay?
What it does say is like that twist and all that are going to have a lot higher risk, even than they had last.
Right, yeah, I mean, yeah, this area here is where we had all the wildfires last summer, just east of the Cascades, and this whole zone, Cascadia, is still going to be high risk in parts of the Olympic Mountains, and the whole ocean shores, the west coast of Washington and Oregon is going to be impacted. So, the warmer weather means drier weather. This figure here is just a larger scale diagram, and basically looking at 2015. I'm not quite sure what all these colored dots mean over here. It's percent of mountain snowpack as of April 1st, 2015, and the idea is to show you that the snowpack, particularly in the west, the Rocky Mountains and Cascades, was dangerously low. Less than 25% of normal are the red dots that you see in this diagram. So 2015 is an analog for the future. Now, if you want to know what the future is going to look like, just look at your calendar from last year and you'll get a good idea. So Pacific Northwest temperatures looked like the mid-21st century from these predictions. The snowpack looked like the end of the century for these predictions. So what are our sensitivities? What broke because of the loss of the water, and can we handle an extended version of this? So this is now a time for planning and adaptation. Okay, so I'm going to end tonight by getting back to that blue marble that I talked about in the beginning and show you something new. NASA last year, not quite a year ago, launched a new satellite called Discover, and it's not a misspelling. It's just an acronym for Deep Space Climate Observatory Mission. And it's a science experiment that was inspired by the blue marble photographs that originated with the Apollo missions to the moon. And the idea is to put a satellite in orbit high enough, far enough away from the Earth, roughly 1 million miles. If you really understand orbit mechanics, and I don't understand them that well myself, but there's a point where you could place an object in orbit around the Earth where it's stuck basically between the Earth and the Sun. And so this satellite has been moved out to that orbit, and there are cameras on board that can basically photograph the Earth constantly on the sunlit side. And so that's what this mission's doing. It's been collecting data for a while, so I have a little animation, if I can get it to play. And you can see something surprising here. Okay, so there's the blue dot, and there's the moon coming across the field of view. And you can see the Earth turning. So, I mean, this is constantly recording the sunlit side of the Earth. The satellite is positioned between the Earth and the Sun, about 1 million miles away from where we are, out beyond the lunar orbit, obviously, and constantly watching the Earth. And there are instruments on board that can detect, sensitive to changes in temperature and the radiative balance of the Earth, so we can actually quantitatively measure the radiative balance of the atmosphere and really monitor climate change from space with this new project. So that's the end of my presentation.
So I would like to ask you, Gary, of all of the information you have, what gives you the most hope where we are right now in these issues?
what makes me most hopeful is that the Paris conference actually got something done. You know, we've been stuck in neutral for so long and trying to take action on climate change, and this is really the most substantive international agreement that's come out of this effort since the Rio meeting, which was, I can't remember, it was sometime in the early 90s. I know, but anyway, I should know this number, but I've forgotten it. But yeah, that does give me hope. I mean, we're actually on track now to consciously take effort to reduce emissions, and that's really the only thing we can do. You know, there's lots of really good science going on, and I haven't really touched much on the space age stuff at all in this talk. It's usually what I focus on, except for, you know, some really neat stuff like this. But you know, there are a number of really interesting new projects and new missions that are coming online. NASA is about to embark on its process of deciding what the priorities are for satellite measurements for the next decade. And so that'll get wrapped up by around 2020, and then we'll have a roadmap of a new series of satellite missions to go on into the future, and what the priorities are, the things we have to measure from space so that we can really keep track of what's going on in the climate. So I think we have momentum. That gives me hope. I think we have good science. We have some innovative new ideas about how we can monitor conditions. The real challenge is going to be coming up with a way to rapidly and efficiently move to a low-carbon energy infrastructure, and that's a big technical challenge, and it's a big economic challenge too. So, but you know, I think everybody knows that the switching to solar is working quite well. There have been a number of incentives in Washington State. We have a good incentive to promote use of solar panels on people's houses and government buildings and so forth. So programs like that are really useful. So moving the technology forward is, I think, you know, the real challenge we have on our plate. But I think there's plenty of reason for hope.
Well, I'm here.
Thank all of you for coming out tonight and your interest, your really sincere interest in this, and your good questions. So it's been a good conversation.
Good night.